This will be the second part of the fourth chapter in this introduction to statistical learning book. We were covering classification in the last meeting, but due to the extension of the chapter, we only got to this part, generalized linear models. So as a quick recount of what we did, basically, ideas we wanted to predict not a numeric value, but a categorical. And when we use tools such as linear regression for the predictions, they didn't quite work, even in cases like the predictions, the numerical predictions, sometimes, despite the fact that they were supposed to model probabilities. So we were supposed to obtain numbers between 0 and 1. We are using linear regression to predict some categorical values, ones represented by numbers, of course. Even in that case, the prediction sometimes lied outside the range from 0 to 1. So the linear regression wasn't useful enough to model probabilities to lie in some specific category. So we covered alternative methods such as logistic regression, linear and quadratic discriminant analysis. But the main idea is that even in the categorical case, there is a special case as well, where what we have been covering is not good enough, and sometimes the predictions for the probabilities aren't what we will. They don't lie. Those numbers don't lie don't lie in the range that we expect them to be. Such scenarios count data. So what you're expecting to predict is something like a number of bikers per hour, some occurrence count. In this case, they consider this particular case to be neither quantitative or qualitative. One may think that it is qualitative, maybe because it seems to be a discrete value, but perhaps it's not considered qualitative because the possible values really are an uncountable one. Well, no, not uncountable. Infinity countable. No, countably infinite of those. Countably infinite. Like the cardinality of the integers. So not as extreme as quantitative, but not the usual finite case for categoricals. So in this case, we are going to see why linear regression fails to be a good enough model to predict discount data. And we will see another type of regression that does match what we want as a predictor for probabilities. And also for, well, in this case, for count values. So let's first start with how linear regression fails with this case of count data. Well, in this case, they're providing some specific examples, but perhaps let's try to summarize it and abstract it to get how is it failing for a more general case, not just the one over here. And the idea we can see it's over here in these graphs. These are the predictions, but despite the fact that we're predicting some occurrence, we get that sometimes the count data predicted turns out to have negative values, where it should always be positive. It should always be also an integer, but at least non-negative. That is a similar hindrance to what happens when we consider linear regression to predict categorical values, because the predictions of this model, they lie sometimes outside the interval from 0 to 1. And sometimes, and something similar happens over here. As we can see, this model using linear regression is predicting negative numbers of bikers at some times, at some specific hours. And another important error that is happening in this case is one of the assumptions that we did in order for us to even attempt to use a linear regression model. Well, the formal term is this over here, but perhaps we can see it more clearly in the graphs. If we were able to use linear regression as a model of these bikers per hour, then we would expect this graphic over here. Let me zoom it a little bit. The graphic over here to the left to be such that these, what do you call it? These blocks, these blue almost rectangles. I mean, they are scattered points, but it's like for each hour, we're getting some rectangle. For example, for this hour 10, the one over here. And in the case for linear regression to work, we would expect that these rectangles for every hour, they have the same width. So that is the dispersion of the predicted value for every hour should be the same. We can see that is not the case because these blue, almost blue rectangles, for every hour, they are changing dimension. Sometimes they are very thin, like for this hour 5 or 6, and sometimes they are very big. That is, the predicted value lies in a very dispersed range, as we can see, for example, for hours 16 or 17. And so this is the condition that it's not working for our model. And they also mentioned it over here, this observed heteroscedasticity is a violation of our linear model assumptions. We should expect these dispersions to be constant for every hour. So like same dimensions of these blue, almost blue rectangles. Let's go to the next part. Well, this is simply a summary of what we just saw. Sometimes linear regression predicts negative numbers for a count. This is a violation that we saw for our model, our linear regression model. And in this case, linear regression is predicting in a continuous range, but we are supposed to be predicting a count. So that is a discrete case. So really, we should only be getting integer values. And what comes next really is the sort of distribution, well, probabilistic distribution, that will not only allows us to work with such specific problems, but it will help us get a clearer picture or how to generalize the type of models that we have been discussing, that is linear regression and logistic regression, because in the end, this part over here, section 4.16, we will be seeing that these three types of models, linear regression, logistic regression, and Poisson regression, they lie in a same category of models where we will go into detail in that part, but really the main idea is that you fix some distribution for the response and then do some transformation in order to fit the expected value of such response via a linear relationship between the predictors. So let's work with this case. As I said, our solution for this prediction of count data is going to come from the Poisson distribution. So really, what is this distribution? Let's see over here. It's a discrete one, a discrete distribution. And this is really the probability that defines it. For K being the possible count in some specific interval, then the probability that this number of counts are seen in such in one arbitrary interval, such probability is this value. And of course, we can expect 0 occurrences, 1 occurrences, or really any positive integer, well, any non-negative integer of occurrences per the interval of interest. It can be perhaps 1 hour as we saw for the biker, so even not really an interval of time, but sometimes even an interval like a region of space or something like that. And in this case, distribution is completely modeled by this parameter lambda. It has to be positive, but a nice property of this distribution, the Poisson distribution, is the expectancy of such distribution. Well, at least numerically, it's exactly the same value as its parents. Over here, they are showing how does this distribution look like if we change different possible values of lambda. So, well, this is the code that generates that. Let's simply look at the graphics. This is k, the possible values of occurrences per interval. Or in the y-axis is the probabilities. And we're simply considering different value for lambda. It seems that if you increase the value for lambda, this peak of the distribution moves to the right. And then again, in a way, it makes sense because you also expect the variance to spread out because the variance happens to be also the value of lambda. So bigger lambda, bigger variance. Okay, so how do we use such distribution that is such PMF, such probability for a regression model? It's going to be, we're going to accomplish that via now modeling the parameter that defines such Poisson distribution, that is this lambda value, and model it after transforming it, in this case via the log function, so that we can have as a guarantee that this number lambda will be positive, because that is remember, this is a requirement for the Poisson distribution. And after performing this log transformation of the expected value of the Poisson distribution, that is lambda, we expect such relationship to be linear with respect to the predictors, that is to the input variables for our model. As I mentioned, the log ensures that this value is positive. Well, I'm not sure about non-negative because you can only take log of positive values. And again, this expression is exactly similar to this one over here. So there is already some semblance to what we did in the case of logistic regression. And that is going to be a little bit more clear in the next couple subsections. So we're simply modeling the parameter now. Let's go to the next question. We're going to estimate the Poisson regression parameters. Really, it's just estimate the lambda. The lambda via using these beta coefficients. So how do we produce a good enough fit in order to conclude which of these beta values are the best for our model? And it's the same idea in the previous case. We are going to define some likelihood function, and we simply want to maximize it. In this case, this would be the maximum likelihood. Now we simply want to maximize it. And once we do that, we obtain our model with the specific parameters undefined. So, well, the parameters now, the coefficients, well, the coefficients of the parameter for our model, the interpretation is going to change a bit to what we were used to, not only in the linear regression case, but also in the logistic regression, because as you can see over here, the formula has changed. This doesn't have the form of a logit. It's now just a log that has a linear relationship with the predictors. So really the interpretation of such coefficients, those beta values, it has also changed. So let's see how has it changed. Well, over there is the answer, but we can actually look at that via this value. Say we fix all the values for x0, well, for x1, x2, and all the predictors, except for the xp predictor. But we now change this value only by 1 unit. So what would be the change in this logarithm once we consider the change of all of this expression when x sub p increases by 1 unit and all of the other predictors remain constant? Well, the change in this right part really is just beta sub p, and over here we would get log of lambda minus log of, well, of the other value for lambda. But remember, when we are taking a difference of log, it's just like the log of the division of their inputs. And once you exponentiate that result, in this case, e to the log of some division, and over here to the right, e to the beta sub p, we get that this part over here, that a 1 unit increase in one of the predictors produces a change of a product of this value to the estimated parameter lambda. Well, over here is an interpretation, but perhaps we are more interested in the general case. And in this case, I mean, we already saw that why linear regression is not a good enough model. And we have presented another one that at least it does seem to be, well, one would suspect that it is a better model because the Poisson regression, sorry, the Poisson distribution, it's already measuring an occurrence for interval. But I will be really sure that this obtained model is actually a better one than the other previous ones. And yes, and over here is why. So let's say the mean variance relationship. As we saw for the Poisson distribution, it has the nice property that its expectancy is precisely the same, well, at least numerically, to its variance. So really, we are assuming about our response variable a quite important property, and that is this one over here. For the case of bike usage per hour, or number of bikes used per hour, we're assuming that the mean bike usage in any hour, sorry, in a given hour, equals the variance of bike usage during that same hour. And really, this statement calls for any of the hours that we consider. So for any hour that you choose, variance and expectancy, they have to be the same per hour. Well, another one was this part over here about the disadvantage of using linear regression, that we were obtaining negative values for predictions of probabilities. But as we assured us over here, when taking this log, over here, when taking this log of the parameter, we assured us that this lambda value was positive. Well, was positive, perhaps not negative as well. I am sure that lambda over here will be positive, and that defines it precisely for what it needs to be for this Poisson distribution. So now the probabilities are perfectly well defined and everything works fine. So the estimated probabilities are also well defined. They lie between 0 and 1. And now comes the part of the generalization of what what we have been doing in the case of linear regression, in the case of logistic regression, and in this Poisson regression. So they will take perhaps a little bit more work to understand, but really it's not complicated. So again, we're using some set of predictors to, well, predict some value. In this case, we are considering a categorical response. No, sorry, some response. It could also be numeric. What we have been assuming is that the response is going to have some particular distribution. We have already worked with the case that we assume that this response, in the case of count data, that it follows a Poisson distribution, but really it can be another one. So now that we have made some assumption about the particular distribution of the response, we're going to transform the expected value of such distribution via what we will call a link function in such a way that this expected value of such distribution, it follows a linear relationship with the predictors. As we did in the case of the count data, because we assume the response to be a Poisson distribution. So first, what is the expectancy of the Poisson distribution? Well, simply it's only parameter lambda, and then we transform the expectancy so that there is a linear relationship with the predictors. And for the Poisson regression, a good enough link function, that is a function that transforms such expectancy. Well, it was a logarithm, in part because it assured us that this parameter is going to be positive. Well, over here, they didn't include the interesting part. So I also wanted to mention it, what they mentioned in the book. So it really is a summary of how this generalized linear model fit into the models that we have already covered, linear regression, logistic, and Poisson. And it is this part over here. So in the first case, linear regression, we're going to assume a link function that is really just going to be the identity. And then we're maybe I should write it, maybe not. We transform the expectancy simply as the identity function, so really we do nothing to it. And this value is what we are trying to model. So in the linear regression case, we simply take the mean of the response, well, the mean of the distribution that we assume for the response, and such mean, we model it via a linear relationship with the predictors. Now, for the other case of logistic regression, what changes for the link function, for the transformation of the expectancy? Well, it is this logic type of expression that we covered. The logarithm, in this case, it could be the probability, and then the complement of such probability. And again, we take logs in order to ensure that the predicted values lie between 0 and 1. So this is a link in the case of logistic regression. And this other case where the link is simply the logarithm is what we just saw for the Poisson regression. The mean is simply lambda in that case. Well, over here it finished. It's the end of at least a part for the book. So because there is enough time, maybe let's take a look at what was added in the cohort. So what are the assumptions for logistic regression? Let's see, I mentioned these links. I don't want to read them completely, but maybe just a quick glance. Response variable is binary. Independent observations. We'll also assume this for the linear regression case. They also cover them. Yeah, they are also going to cover them over here. So let's simply read them in this part. Okay. Logistic regression when the response is only a categorical variable with two possible values. So something like yes or no, or male or female. Well, that is precisely the first assumption. The response variable has only two possible outcomes. The second assumption, as I said, is really the same one as in a regression, and that is the observations are independent of each other. But they also mentioned over here that they have to be identically distributed. And again, it's really the same test as we saw for linear regression. The plot of precedence against time. If it looks like a constant, then yes, such independence can be assumed. If not, then no, this assumption hasn't been covered. A third assumption for logistic regression: no multicollinearity among the predictors. That is, if two or more explanatory variables have some high correlation between each other. However, I mean, we can deal with such fact if you use PCA, or maybe it isn't necessary to even use PCA if you know that the information of one predictor, and really you don't obtain anything else if you don't consider it, because perhaps such information is already contained in another predictor that you're working with. But if that is not the case, then still PCA can handle a little bit of this possible issue. As in PCA, we will only cover it in the last part of the, well, maybe not in the last part, but in ISLR1, I think it was in the last part. Now, this fourth assumption is in the case of no extreme outliers. Well, about this fact, I just saw recently that there are different type of fitting criteria that some of them help you better. Now, well, at least on the usual one of mean squared error for this case of dealing with outliers. Of course, such is not the case for logistic regression, because we are considering a fit via maximizing the likelihood function. But in the case of linear regression, then it happens to be the case that if you want a better handling of the outliers, a different type of fit, so not something like mean squared error to fit your parameters, but something like only consider the absolute value of the errors, then in that case, such type of fit does produce you a better handling of these outliers. So if there is something analog to that for the logistic regression case, and maybe that could also be like not a complete solution, but like perhaps some change in your logistic regression fitting, so that we can handle a little bit better the assumption over here. And let's see the fifth assumption. There is a linear relationship between explanatory variables and the logit of the response variable. Well, yeah, because that's simply our, well, it's really what it says over here. That is the precise shape that we are expecting for our model prediction. Sorry, for our model probabilities. So that is this. I don't know if they performed the. They didn't have a graph. So that is really this S curve that we are looking, that we get in the logistic regression case. Turns out that there is a test, well, a specific statistical test in order to check the assumption. Let's see, it comes from this. Over here. Over here, I'll simply consider some data of the Titanic dataset. Well, they're simply cleaning it up, now performing a logistic regression for for predicting if the person in the Titanic survived or not as a function of the age of the passenger and the fare of and the price of their ticket. But now over here comes a part for the test. This for the well, I don't know this part. I mean, they're simply adding one to the age column and one also to the fare column in order to fit it into this well, a statistical test. But I am not sure why the necessity to add one to the predictors. Why not simply use the, let's say, raw data once that it has been cleaned? And the last assumption is that, well, for logistic regression of a binary response variable, is that the sample size must be sufficiently large. If not, then really the conclusions won't be valid enough. And over here they provide a rule of thumb. So they say you should have a minimum of 10 cases with the least frequent outcome for each explanatory variable.
Lucio?
Yes.
For the previous part, the box Tidwell test, was that for testing the collinearity?
They were testing if the logit had a linear relationship between the explanatory variables.
Oh, okay.
So really, if let's see. Over here, if this expression really was good enough, so that if there is really a linear relationship between the predictors and this logit transformation.
Yeah, I'm not familiar, but like you were saying, the +1 has to do with that.
Well, I mean, both stated. Well, I looked it up and then share it in the Slack.
Thank you.
So really, the last part over here, a rule of thumb, a minimum of 10 cases with the least frequent outcome for each explanatory variable. Well, that is really something to expect. I don't mean about the specific number of 10 minimum cases, but that once you have your data, that you then are going to try to build a model out of it. Well, you should expect it that such data is representing the actual proportions in the population, right? So if you're really missing like some of the least common cases for the response variable, then that is going to force a little bit your model to produce even a lower estimate of what is the probability that one observation lies in such a specific category with low probability. So it's going to make such a probability of such a specific category to be even smaller than what it already is. So really, this comes back to the fact that your sample should be representative of the population. So really, all of the possible cases of the categories should be covered. So at least some cases for them. Really, that's it. Well, we are not covering the labs. So what we will be looking at next week is going to be the exercises for this chapter, the classification chapter. And after that, there is going to be 2 weeks of break due to the daylight time savings. So if there's any question or comments before closing up.
No, thank you, Lucio. That was great.
Okay, well, thank you, Derek. Bye.
See you.